Hey guys, sorry about the technical glitch, all right, through class today. So temporarily, till we can get a little bit better with the internet access, I'll record some stuff for you guys just as backup if the stream isn't going so well. So what we were talking about today, right, depending on what class period you're in, was the next step that revolves around the atom. Right, now, don't forget, if you're in period 1, you have a test on Tuesday. If you're in period 3, nothing to worry about. Period 4, you have a test on Monday. Right. So this information that you're going to see here is new info that is not on the test you're about to see. Right. This is all for next chapter. Right. So some of the stuff that ties into what we've been doing, though, is that all of this new things we're going to cover revolve around the atom. So hopefully between now and when you have your test, you understand that there's different subparticles in the atom. All right? Some of them live in the nucleus. So you get your nucleus of your atom. We know that the positively charged protons live in there. We know that the neutral neutrons live in there, right? In varying amounts depending on the element. We know that electrons live on the outside in the electron cloud. Some other things, hopefully, that you guys will learn is about size. We know the nucleus is very tiny, but it comprises of all of the mass. All of the weight of the atom is in the protons and the neutrons. All right, so these are very heavy. The electrons out here, by comparison, are essentially weightless. Not really, but whether I take an electron away or I leave it there, it won't affect the mass of the nucleus in a measurable amount. So all those numbers that we learned from the periodic table, average atomic mass, whether the electrons are there or not, those numbers hold true. So all we do to get the mass is the protons plus the neutrons. The electrons don't really affect it. But the trade-off is the electrons get to move anywhere that they want. They're out here moving around in the electron cloud. So different people found those different parts, right? You had J.J. Thomson discover the electron. Robert Millikan figured out how heavy it was. Rutherford did the gold foil experiment that discovered the proton, right, and the nucleus. And James Chadwick discovered the neutron. But then a question arose based on some other physical principles that we know. One of those questions was, we know that electrons are negative and protons are positive, and we know opposites attract. So there should be some sort of attraction between the negative electrons and the positive nucleus. The other fundamental principle that we know is that smaller objects gravitate toward bigger objects, like the moon gravitates toward the Earth is in sun's gravitational pull, and we know that the nucleus is immensely heavy by comparison. So the question started to become is, why don't these electrons simply crash toward the nucleus? Why are they able to move around so much? And that's what the next chapter is all about, right? So it gets this fancy name, right? It's called quantum theory. And in the Google Classroom, there are the notes to this. There's a big PowerPoint, right, that you guys can reference. And that if you can print out, you can mark it up. All right. Quantum theory is simply trying to answer a simple question. That question is, where are these electrons at? Quantum theory is about trying to pinpoint where the electrons are in the cloud and why is it they aren't crashing into the nucleus. Those are the two fundamental questions. So it's nothing crazy. It sounds all heavy and crazy, but it's not. It's just, where are the electrons at and why don't they crash into the nucleus? So one of the first ideas that came out was that maybe electrons aren't particles, but waves, because particles have different characteristics. For instance, Particles can move around, right? They can exert force, which is why when I do this, you hear it tapping. All right. And if they tried to pass through, right, a window, boom, they'd hit the window and bounce off, right? That's particle nature. Waves have different rules, right? Waves have energy, but they don't transfer, all right? When they hit objects, they reflect, all right? They refract at times, and they can go through certain objects like a glass window. The sunshine from outside can come through. So class started off talking about some characteristics of waves as a friendly reminder of what those are. All right, so we went into our PowerPoint at that point. So I'm going to share my screen with you so you guys can see that. All right, and we dove into this and we said, okay, we have got quantum theory and electronic structure. And the idea that we went with here is that a lot of substances can move like waves. Light is one of them. Like they give it a fancy name. It's called electromagnetic radiation, the thing you see right there. Electromagnetic radiation is just a fancy name for energy that moves like a wave. And depending on what the wave looks like, we change the name of the radiation, right? So I listed all of the different types of electromagnetic radiation, things like X-rays, radio waves, ultraviolet, UV, microwaves, infrared, then visible light. And what makes one of these different than the other is what the wave looks like. So we know that there are some high energy waves and some low energy. And what we did was we jumped to a website that let us look at that. Right? So here's our wave. Right? We started off looking at a wave that looked like this. That wave, very long, doesn't occur that often, very gentle. That's a wave that you would not be afraid to be hit by. Those waves get names in their radiation, right? That would be something like a radio wave. Right? We're not afraid of radio waves. Right? That might be something like what we call a long wave. But as we change the intensity of the wave, how often it occurs, which is known as the frequency, right? The wave's name changes. Now, that wave right there, if I pause it, isn't really one wave. You've got a couple. One peak, two peak, three peak. We know there's multiple waves in there. The other thing we know is that this wave is more complicated than the first one. So it's a higher energy wave. Right? There's more of it jammed into the same area. Right? So distance between identical points on a waves, top to top, bottom to bottom, for instance, that's known as the wavelength. So the shorter the wave gets, the more frequently it occurs. So those are indirectly related. One goes up, one goes down. But if you look at this wave, definitely higher in energy, but still not super crazy. That might be something that's higher in energy on your scale, like infrared or visible light, but something that we're still not afraid of hurting us. Right? But if we go back and we intensify our wave even more, that wave is clearly possessing a substantial amount of energy, right? And if that wave were to hit me, it might do damage. So because it's a higher energy wave still, we are now pushing up into things you know aren't good for you to absorb, like X-rays, ultraviolet light, which can give you sunburn, right? And gamma rays, which is what you get when you have a nuclear fallout, okay? So the wave dictates the name. So I know it sounds crazy, electromagnetic radiation, but just think of them as different waves that get different names. And then we went over some of those terms that we talked about. We said there is wavelength, and that's the distance between identical points on two waves. There is frequency. It's how often the wave occurs. We went on to talk about the labels for these. The abbreviation for wavelength is the Greek letter that you see here, lambda. The abbreviation for frequency, we'll keep it as a V for simplicity's sake. Right? Technically, it's not that, but don't worry about it. We'll say frequency is V and wavelength is lambda. But it's also important that you know the units. So what we did down in this area of the slide was we said that wavelength gets measured in meters and nanometers. Those are the two units we tend to see for wavelength. The distance from the peak to the peak tends to get measured in nanometers. The frequency, right, gets measured in a unit called hertz. Right? So down here we wrote measured in hertz, H-E-R-T-Z. Right? Then what we did was we said we know some of these waves are high energy and some are low. So the more frequently the wave occurs, the higher energy it went. So for this guy here, number 2, he's pretty intense. Maybe he is an X-ray. The bottom one's the least energetic. Right? He's probably something safer. Radio wave or a long wave or an AM wave. And then we just knew this guy was somewhere in the middle. So we went through a little exercise in class where I had all of you guys propose a set of 3 and what they could be. But the moral of the story was your highest energy wave had to be number 2. Your lowest energy wave had to be number 3. And number 1 had to be somewhere in between them. Right? And on the scale, there were a lot of different options. From there, we moved on to, well, how do I know exactly what that's going to be? And what happens is if I zoom in on this guy, you can see this scale down here. There's number values associated with the wavelength and the frequency. So it seemingly became important of, well, how do I calculate what that number is? Right? So we got into some math equations that let us do this. And then on this slide, I gave you some tips that would help you with that. Tip number 1 was reminding you what the labels are. Frequency gets measured in, and I'll type it for you guys, hertz. Wavelength is meters or nanometers. And then lastly, this C shows up. And C is the speed of the wave, all right? But most of the time we treat it as a constant. We treat it as the speed of light, which is 3.00 times 10 to the 8th meters per second. So when you look at the examples here, obviously we're doing some math problems. Right? The thing that you need to recognize with this is that we have 2 styles of solving stuff in chem class. Right. Style number 1. I'm going to stop presenting so you can see me again. Style number 1 is what you guys are going to have to do on your test next week, which is the whole bracket problem. List what I know, put it over 1, draw my brackets, unit to cancel on the bottom. Excuse me. Unit to desired unit on top. The other one was what we did last chapter, which was the density style. And those ones looked a little bit different. What we did was we looked at a number, we pulled it out, and then we labeled it with a letter. So when it was the density, mass, and volume, we knew if it was grams, it was measuring mass. If it was liters, milliliters, cubic centimeters, it was volume. And if we were measuring density, it was grams per milliliter usually. The same rules apply for this equation. It's just the labels are different. Right? So when I looked at that first question, right, and that first question, right, is on slide 5, so you could be looking along. it said, what is the wavelength of a wave in nanometers if it has a frequency of 6.21 times 10 to the 14th hertz? So the first thing I'm going to do is pull that 6.21 times 10 to the 14th hertz out. 6.21 times 10 to the 14th hertz. The label tells me what its abbreviation letter should be. Hertz measures frequency. Frequency is the letter V. That's why I'm going to say V equals 6.21 times 10 to the 14th hertz. I'm all out of numbers. So then it was list what you're looking for. And the question said, what is the wavelength? And the abbreviation for wavelength is that Greek symbol lambda, right? Lambda. All right. Then what I do is I find an equation that has these two things in it. So we have an equation that has lambda and V. C equals lambda V. The only thing is, though, is C is there and I haven't listed it. So I have to put it over here. And the reason we didn't see that number in the problem is it never changes. It's a constant. Right? C represents the speed of the wave, which is 3.00 times 10 to the 8th meters per second. So I go and list it after I realize I need it for the equation. Like from here, what we do is we put a box around our question mark variable, which is the wave. I need to get that by itself. Right? So what I'm going to do is algebraically isolate this like it's x. I see times v, so I'm going to divide both sides by v to cancel. When I do that, I'm going to get lambda equals c over v. Right? Before I plug in, I have to make sure I see two labels that will cancel. And it doesn't look like I have them. Meters, seconds, and hertz. But we made a note on this slide at the bottom to say hertz and seconds can cancel. And the reason is that hertz is really 1 over seconds. So we can cancel a hertz with a second because you end up getting seconds over seconds. You don't need to know all that. Just know hertz and seconds can cancel. That means I can just plug these in. I pull C down, put it in here, 3.00 times 10 to the 8th meters per second. I pull V down, which is the 6.21 times 10 to the 14th hertz. Those can cancel, and I end up getting 4.83 times 10 to the negative 7th meters. Okay. That's a wavelength. Now, here's the catch. If you look back to the question, which I'll share with you, sorry about that. You look back to the question. In here, it says, what is the wavelength in nanometers, right? And the reason they want it in nanometers is because if we want to get the color, look back onto this chart. If I zoom in to that color scale, what you'll see down here is it 400 nanometers, 500 nanometers, 600 nanometers. Right? So I need to get it in nanometers so I can compare it to my chart. And right now, we're in meters, right? So that's no good. Right? So we've done these before. I just want you to understand that's why I'm doing this. We got to convert the 4.83 times 10 to the negative 7th meters into nanos so we can use our chart. So meters to nanometers. This is written on the sideboard, but this is one you don't need to memorize. 1 meter has 1 times 10 to the 9th nanometers. Right? So we do our math, and all it does is swing the decimal, and it makes it that number that's more manageable, 483. Then what you do is you scan on your chart till you get to 483. So if I share that with you again, what we would do is start down here. We're at 400. This is 500, which means this mark here is 450. So we're somewhere up in this range, which we would say, you know what? That is going to appear to me as bluish green visible light. My eye would detect that as the color blue-green, that particular wave. So that was the first problem we did, right? Then we dove in to the second problem, right? And the second problem set up similarly, but was asking for something different. It said, what is the frequency of a wave if it has a wavelength of 4.76 times 10 to the negative 9th meters? So what I did was I first pulled out the number, and the number was the 4.76 times 10 to the negative 9th meters. Then I figure out what letter is that. Meters measures wavelength, and wavelength gets the lambda for its symbol. No more numbers, and then it asks me my question. What is the frequency? So question mark, frequency's letter is V. Right, so we do that. Then again, we find the equation that has lambda and V. That equation is C equals lambda V. Then a new letter showed up that we didn't list. No big deal. C never changes. It's the speed of light. 3.00 times 10 to the 8th meters per second. Put a box around what we're looking for. This time my question mark was around the V. So I got to get V alone this time. This means that instead of dividing by V, I'm going to divide by the other one, lambda, to get that alone. So V equals C over lambda. All right, before I plug in, have to make sure that I see two labels that'll cancel. I see meters, we're good. I'm going to plug that in. So I get 3.00 times 10 to the 8th meters per second. I get 4.76 times 10 to the negative 9th meters. My meters cancels. Trickiest part about this one is it looks like my answer is going to be seconds, right? Because that's the label that doesn't cancel. But it's in the bottom, right? And when seconds is in the bottom of the fraction, we don't call it seconds. We call it the frequency unit, which is hertz. So you've got to remember that frequency should be in hertz. You do the math on this one, and if you punch it into your calculator right, you get 6.30 times 10 to the 16th hertz, because I just do the 3.00 E8 divided by 4.76 E9. I didn't ask it in the question, but I could have. If I give you a chart of frequencies, I could ask you, what form of radiation is this? That chart is in your PowerPoint. It's just a little further ahead. So if I bring that back up and we keep scrolling, here's a frequency chart. Right? So down here, we can see what our frequency exponents are. So we're not 5, we're way up at 16. So we scroll up, we're at 16, right? And we're in between 16 and 17 because our number was 6. So we're kind of walking this line right here. If you said it was ultraviolet or an X-ray, gamma ray, I'd give you credit. In reality, it's probably an X-ray, right? Who's living right around that line. All right, so that was pretty much class in a nutshell. I know we've got access points coming soon. Hopefully the live stream will start going better. I feel bad that you guys have to watch the video, but I'm happy to keep recording them because the big thing is that you guys get the information. Please don't hesitate to email or Parent Square a message with questions, things like that. With regard to the test, what I'll do for each of you guys that are still having to take them in 4th period. And first, just like always, for you 1st period guys, I'll drop it onto the Google Classroom when everybody else starts testing. Same is true for you guys. You won't see it there. When I pass out the test to everybody in class, I will drop the exam into the classroom so you can access it. and then all you have to do is answer it on a separate sheet of paper, and then go ahead and send me a picture of it in an email, and I'll get that graded for you. I hope everybody has a great weekend. I hope this helped out. Again, stay safe, stay healthy, and hope you guys have a good one.